Okay, I'm Jim Geddes. This is a talk that I'm going to pilot on you. It's a talk I'm going to be giving at the Prague IETF meeting in the transport area meeting, not just a working group. This is a very serious issue. Some of you may be aware of the blogging on Bufferbloat that I started in late November, December. And it's dismayingly big problem. So the intent here is to try to wake people up, because it's a mistake we're all making. I've been mostly assembling puzzle pieces, and I'm sure you will have seen many of these pieces of this jigsaw puzzle yourself, but I don't think many people, the overall picture is what's new and frightening. I have to acknowledge, obviously, where I got most of the pieces, though I came with a few. I don't have much time in Prague, so this is a very abbreviated version of a much longer talk that I gave in Murray Hill in January that's already up on the web. So the intent is to go through this pretty quickly and then open up for general give and take, because that's exactly what the area directors want at the IETF. So you need to please understand that there's a fundamental presumption that's built into our existing transport protocols, not just TCP. And that is that the network will do something in a timely fashion, whether it's packet drop or ECN, which is not widely deployed at the moment. It's not supposed to take forever. This is a real issue, because if it doesn't happen in a timely fashion, it literally defeats congestion avoidance. Absolutely, totally defeats it. And these days, the network is, particularly around the edge, is almost always badly congested. Another point which many people miss is that, particularly given that ECN is not deployed, we have no alternative at all, packet loss is actually correct and normal and essential to the behavior of congestion avoiding protocols. If you lie to them, they don't like it. We use TCP as a touchstone for these protocols of saying, if you want to deploy a protocol on the internet, you better do at least as well as TCP as avoiding congestion. So what happens if TCP's timeliness assumption is violated by a lot? And that's happening by buffering. I heard this for years. Many of you, particularly the older ones who share a broadband link with a family or roommates, know this refrain very much. You know, the internet is slow today. Yeah, literally, the internet is slow today, Daddy. And I've heard this for years. Every time I try to debug it, and I tried to debug my home network on at least 5 different occasions over the last 4 or 5 years, without success until this last summer, it would stop misbehaving. Though sometimes I could sort of get it misbehave for a while, but then it would evaporate. So my personal piece of this really starts last April, when I was doing some very simple tests of an old piece of hardware to prove that we shouldn't spend any more time on it. And I noticed this strange behavior, 1 to 2 second latency and very high jitter. So at the time, this is last April, I was wondering, could this be something having to do with Comcast Power Boost, that sort of thing. So what we're looking at here in this particular case, I'm going to be using the same map again and again, just because otherwise I'm going to be talking about things all over the internet. The problem is that widespread. And you'll get lost about what I'm talking about without the map. So in this particular case is actually very close to what I ended up doing. I had a machine down at MIT, and only a few more hops than are indicated in there, and then I have a local cable modem in my house, and I ultimately, to eliminate my home network, plug directly into that cable modem for debugging purposes, though usually I have a router. And all I was doing was monitoring latency while copying a file. So in July, having wondered, I had real trouble reproducing this. I've been having problems with lightning. I've had 3 lightning strikes near my house in the last 2.5 years, which meant I've just done tons of debugging and so on. So I'm trying to reproduce this after the 3rd of these lightning strikes, and I'm having some trouble. But just before having wondered about Power Boost, I decided to try to track down somebody who could tell me definitively what was going on. I work on immersive teleconferencing, and if I don't have good latencies, I can't do teleconferencing. It was vital for my job that I understand what's going on in my home connection. So I had lunch with a gentleman at Comcast, and we had a very wide-ranging discussion that day. We hit it off. He's a great guy. And so he gave me a bunch of puzzle pieces that he hadn't fully assembled. And along the way, I told him I was having some network trouble. But it wasn't really till actually the day after this that I got the real smoking gun. But one of the things he suggested was what he called the big buffers problem, which he'd been chasing on suggestion of Dave Clark at MIT for some years, but hadn't gotten good proof of it. And he said, well, we can eliminate whether it's turbo boost or not by the signature of the difference between a DOCSIS 2 and a DOCSIS 3 modem. They have different bandwidths, and you can get different data that way. And I'll be able to definitively tell you, is this Power Boost or something else? So I tried this, and again, I've had lots of problems in my home network, including the cable up the hill. So I hadn't even trusted it. So he suggested that. He also noted that the RED algorithm, which is commonly used for queue management, is often not turned on a lot of production networks. That was a surprise to me. I mean, I've been aware of RED. I usually burn packets. I'm an applications networking person. I've been burning packets from the X window system to HTTP for a long time. So I've been aware of things like RED for a long time. I lived through the 1987 collapse of the NSF net. So I've been very sensitive, but this came to me as a surprise. Other problems like, he told me that, and he said, well, also ECN is actually blocked in some networks, and I got later good explanations for why. There's some broken kit that was shipped in some quantity like a decade ago that will just crash if it sees a packet with ECN in it. So some network operators have just stamped on the ECN bits. There are also other things that happen. The bits being used for ECN have a long and checkered history. And so there are other reasons why people have stepped on those bits, sometimes by accident. He also said, hey, you should go look at the ICSI Netalyzer stuff. If you guys haven't played with Netalyzer, do so. It's now the first thing I do anytime I use a new network. Okay? And it's already told me that Bufferbloat is in your network here, and the rest of the network actually looks pretty good. It tests many, many, many different things. DNS port randomization, you name it. It's a wonderful tool.
Is it open source too?
No, it's a Java downloaded applet, and I've had some arguments with Vern Paxson that they should make it open source. They're mostly worried about support issues. So the day after I met with Comcast, I'd already come across smoke ping as a way to monitor this. I was copying the old X Consortium archives from my home machine to a machine at MIT. And this is the output of smoke ping. So I was seeing over 1 second latency, and these little momentary periods are just when I got so sick of how badly the network was feeling for web surfing and or dealing with mail that I would suspend the copy a couple times. Okay, so now I know I have the smoking gun. Can trivially reproduce this. So after some fussing around, because it's been over a decade since I was in the packet capture business, I captured some traces of a very simple file, SCP of an 80 megabyte file from home to MIT, and wasting another week or so determining that Tim Shepard's XPlot was still the nicest way to look at it. I got this out. And for those of you who've never looked at, never played with XPlot or whatnot, it can display lots of different interesting things. As I said, in my full version of the talk, I do more of this. But the interesting thing is this red, this instantaneous outstanding data. What is it? This is saying something about what the window is believed to be, right? Why is it doing this funny thing? Now these are like 10 seconds apart. A TCP sawtooth on a 10 millisecond path should be way less than that. So I saw this and went tilt. This looked like no TCP trace I remembered when I was working in HTTP in the 1990s. And in fact, the first reason why I did that was just in Wireshark. I go through it, I could see these huge bursts of duplicate ACKs, and then bursts of retransmits, lots of SACs on these long time scales, of order 10 seconds. So, just nothing I've ever seen. So the next week, I went down to Murray Hill, and so I was at my in-laws' house, who live about half a mile, or I stay with them when I'm down there. And so I have an almost identical setup, except this time it happens to be FiOS rather than cable, okay? And happens to be a different major piece of the internet, but it's like a 20 millisecond path from the local head of the FiOS to MIT rather than 10, but it's not a very different network. And I look at some data, and I see a almost identical sort of thing going on. The period's slightly different, but the signature is almost identically the same. I didn't have the password to the router, so I couldn't have the rest of the family get off of it to get a completely clean trace. But again, if you look at having a 1/4 megabyte of outstanding data on a 20 millisecond path, the bandwidth delay product you need to saturate that is way tiny less than that, right? Why should I be seeing 200 milliseconds of latency? Okay? Complete bogosity. Okay? And then I do the same thing, but on the wireless side. And of course, this is much rattier because there's lots of more interference and the like. And I'm observing stuff that's way more than 400 millisecond times. You can see some full slow start restarts on this. Very high packet loss rates, but again, horrible latency. You guys have all suffered from this wherever you go too. So, some of you may be real TCP experts. I don't know whether any of you are here, but certainly at the IETF there will be people who really are, and I'm not. So I called in the fire chiefs or consulting detectives, whatever you want to call them, to look at my traces. Okay? what's going on here. You know, I sent mail to Dave Clark and Dave Reed and Vern Paxton and Dick Seitz and so on and so forth, and also Van Jacobson. They looked at this. Van even says there's timestamps in my traces that I didn't know even existed that proved the case. And that what's happening here is in fact defeating congestion avoidance. So what you need to understand is that when you have buffer bloat, if it's of any substantial size, you have destroyed congestion avoidance in the transport protocols. Not a good situation. Various kinds of classification can't help you right now at all because these are dumb devices. If you've got a second of queue in a cable modem, as I did, more than a second, once the packet goes in, it's going to come out that second later. So you know, you've been had. You can't try to work around this. Okay. Now there are ways you can use traffic classification to your benefit. I'm not saying it's a bad thing, but you fundamentally have to worry about buffering in the first place. Now, what kinds of things trigger this? Well, it's actually very simple. Anything that saturates the link, okay? So that's things like uploading a new video to YouTube, or I caught Google Chrome updating a crash dump of itself to Google one night when my network went out to lunch, or you mail a bunch of big images to a friend, or you happen to be running BitTorrent, more about that later. Copying files, as I was with my smoking gun. Backups. Downloading videos to a disk so that you're saturating it. Potentially video teleconferencing at times. More insidiously as web browsing can even do this, for reasons I'll go into a little bit more later. There's a that's sort of a quick bit to it. Well, what happens when you've got bad buffer bloat? Well, it isn't just that your latency goes bad, but things start to fail because the latencies are so large that the timeouts start to happen. Okay? And there's also higher packet loss than you should be seeing. Even worse, bursts of packet losses. So your DNS can fail at times. ARP, DHCP, RANND for IPv6. The thing you have to understand is that these other protocols, which may be a tiny fraction of the traffic, had better get through for the network to function well. Okay? If you want voice over IP, the classic number you need is really wants to be low. The most acceptable is of order 150, and you want it to be much less than that, right? If you like playing games, you're going to get fragged a lot. So in any case, everything sort of goes to hell. Now, as I said, there's a wonderful data set from the ICSI Netalyzer group. It's a group of network research group in ICSI at Berkeley who have for more than the last year been taking data. Now, let me help you understand what this is saying. You can see various horizontal structure in the dots. That's what the provisioned bandwidth is, okay, in the uplink and downlink. And you can infer what the buffer capacity is by being clever on your tests. This one happens to use a UDP-based, this does a UDP-based test to saturation. So you can figure out what the size is. Well, if you know what the bandwidth is and the buffer size is, that translates directly to latency. Okay? This, guys, is half a second. This is 1 second. This is 2 seconds. This is 4 seconds. And for reasons that I don't think I know, maybe ICSI does now, they don't see anything beyond 6, probably because too many things just break entirely. And of course, where you want to be for good VoIP is actually down. If this is half a second, we need to go to a quarter second to a tenth of a second. Okay? Something much more dramatic than this for good VoIP. And the other gotcha is that at the time that most of this data was taken, Nettalyzer was under detecting buffer bloat, particularly on higher speed lines. The different colors are for the different technologies. So you can see that there are problems in all of the technologies. Okay? All the commonly used broadband technologies have problems. The only question is really what degree. I can't tell you whether it's half. I can't tell you whether, but it might be 90%, it might be 30%, but it's bad. Okay? You can walk out of here and know that our commonly used broadband internet connections are broken. That case has been proven by ICSI. Okay? Vern Paxton, Christian Krybach, Nick Weaver, and I'm forgetting the fourth person's name. Unfortunately, I've got very paranoid along the way. And I'll continue and convince you to be as paranoid as I am. It is almost everywhere. Okay, so I'd seen some funny things in my home network along the way. So we'll concentrate here, either good old conventional 802.11 or wired Ethernet. So for example, one day, I think this was like in September, I caught Smoke Ping telling me this about my home network. How would you like to have 8-second latency? Okay? I could go back and reproduce this and make it as long as you like, as I did for the other smoking gun, but I didn't want to bother. Again, same simple thing. This was using a recent commercial home router with 50 megabit downlink, 10 megabit uplink on Comcast. As I said, I don't care because I can reproduce this on anything you like, and I'll explain exactly how and where. So this is clearly nuts. Okay, so I tried several different commercial home routers and got the same sort of thing. So eventually I got around to playing with installing OpenWrt on a router so I could understand what was going on better, log in and tweak at it. And I'd realized that Linux's transmit queue might be a problem. So I twisted the transmit queuing knob, nothing happened. Pulled out some more hair for a couple of days and realized, well, of course, I'm copying from my laptop upstream, so the queue's on my laptop, not in the home router at all. Okay? And so you say, well, it's never going to happen. Well, it does happen all the time. Anytime the broadband's bandwidth exceeds the wireless good put in your house, you will have this case. Okay? The bottleneck in the typical path will have shifted from your broadband connection to your wireless to your router, home router. Happens to be common in my house. I got a big chimney, and so I see this more than many, but all you have to do is walk a little bit further away in your house or walk outside and get your bandwidth down and you'll see this, at least on current hardware. So, where are our buffers? These days, most home routers are often based on some flavor of Linux, but sometimes some other operating systems. So in Linux, there's a transmit queue, which, among other things, is where we do packet classification on Linux. Unfortunately, the default is now typically 1000. You can all just type, go look at using IP or ifconfig, and you'll see that the typical number you have is 1,000. That's 1,000 packets, guys. Then there's sometimes some buffering in device drivers. So an example of that is OLPC's wireless driver. Dave Woodhouse found it convenient to have one extra packet that he could buffered internal to the drivers, so he wouldn't have to deal. That made his locking much simpler between the top half of the system and the disaster he had to deal with out on USB. Our hardware guys over the last decade have been blessing us with these transmit and receive rings. On current Ethernet and wireless hardware, these often support up to rings of 4096 packets. And the default, by the way, seems to be about 250, of order 250 packets, and that seems to be roughly true on more than one operating system. There may also be some additional bufferings inside the device itself. I'll again use OLPC, where the mesh module has 4 packets of buffering out there. It needs to have some buffering. Some buffering is necessary, just that sort of thing. So let's do, and I have some theories that there may be some other places where buffers may hide, but that's sort of the basic list. So if we do a simple calculation, presuming 10 megabits per second, 256 packets is about 3 million packets, so there's a third of a second one way. But what happens if you're at a busy conference and your fair share is 100 kilobits per second maybe, or a lot less than that nominal 10 or 20 megabits you think you have. You often don't. You certainly don't here at the moment, unless I have all of you in rapt attention. I hope I do. An interesting thing to think about is that people just sort of time out. So what's happening here is we're causing the load to go away by people timing out rather than the protocols timing out. People get so bored they go do something else. There is an upper bound on latency that people will tolerate. And things start to fail because there are various timeouts in various protocols. So there isn't a sort of upper bound of latency. So you might say, well, why don't I see Bufferbloat on Ethernet? Well, in fact, you do. So just saturate the connection again. I just want to make sure I could do so trivially. I happen to use iPerf or whatever like that to do it. And so I took my 1 gigabit NIC on this laptop, plugged it into a 100 megabit switch, and what happens? Well, you can trivially saturate it, and you get about what you would expect, which turns out to be about 10 milliseconds of latency. Okay, from that. That's, by the way, having turned TXQLN down to 0. Okay, that's just the 256 down there. It turns out that as far as I can tell, Windows has a clever hack in it, which is that it never, by default, goes faster than about 85 megabits a second, and therefore it won't saturate the most common Ethernet switch out there. So you typically don't see this on Windows. But sure enough, if you take current hardware on Windows, plug it into an old 10 megabit device, or force it down to 10 megabits, then boom, you see exactly what you expect. So again, there's the buffers in the device driver. Okay? And there's a tech note explaining why Microsoft bandwidth shapes to this. And they say to get better multimedia experience. I think by which they probably meant that now their scroll bar for going through different parts of the video would actually behave again, because they were no longer in bad things. So I think they did a very pragmatic, clever thing without fully understanding what happened. Okay, so where does host buffer bloat hurt? Well, since our routers are running general purpose operating systems, we got it there. We got it down in handsets. We have it obviously in our laptops. We can have it obviously on that end of it. Usual sort of place. Okay. What happens if there's lots of buffering all over a network? Well, what you're basically back to is classic congestion of the 1990s. You don't have any queue management going on to control your latencies, which if you have red enabled in a core router would keep the situation from going nuts. So your latency goes up when it's loaded, but at least on 3G, you don't see much in the way of packet drops having to do some stuff on that. What you would expect in that case is exactly what you see. You see a daily pattern in a congested 3G network where I've personally observed 6-second latencies. Dave Reed has seen up to 30 seconds. I now know it to exist in the radio side of things. Van Jacobson says he has data that remember, the bottleneck in the path can be different in the different directions, okay? So he says he's also seeing it observed in backhaul networks, the networks that connect the final radio link elsewhere. Exactly where in those things, is a different question. And I don't exactly understand how all the backhaul works in the 3G stuff. I now work for a company that builds this gear, so I'll probably know more in a while, but I've just really started those discussions with the people who understand that stuff. This is not a new problem. In fact, this goes back, it was first seen in satellite links in the 1980s. Remember, it isn't just buffers, it can also just be delays. So in 802.11 there's some wonderful things about, well, let's transmit this again and again. That turns out to be inserting delay, and that has the same effect. So we have this problem in that, and it's the same class of problem in that. So as I said, I was very surprised when I was told that a lot of networks weren't running with AQM. And so last August, I picked up the phone and called Van, who I knew from the 1980s and 90s, run into once in a while since then. So Kathy Nichols walked into his office a little over a decade ago, and in the course of 2 hours, proved to him that there was not one but at least 2 bugs in red. And it has exactly what we now know to be the case. You have to tune the thing for it to be effective, and tuning that can be difficult. And it can hurt you if you get it wrong. So there are a lot of network operators who don't bother to configure it. So that nagging question got answered. There's more than 100 papers about tuning red in the intervening decade. Van tried to publish this at least twice. There are a couple of very funny stories having to do with that. One of them was that he used as a physical analogy to what was going on a flush toilet. And one of the program committee members was offended by that one time, and the other time it was a blind review, and the reviewer said, in their review said, this paper can't possibly be correct, the authors should go read Floyd and Jacobson. So an early version of this paper did happen to escape. It's called Red in a Different Light, and I hope that there'll be a finished paper sometime soon. I have a draft of it on this laptop, but I don't know whether it has all the bugs fixed. I don't even know at this point. Van also pointed out in this and subsequent conversations that you have to think about congestion not as just a steady state thing. You have to think of it as time-based phenomena. And we have, not only are we seeing these spiky behavior in TCP, but it turns out in a lot of the broadband and wireless gear, there's various things that are gathering up packets and then gathering up and then shoving them out in bursts, in periodic behavior. So the worry is and it has been seen in the internet at other times, is if there is something that happens to cause us to self-synchronize, we could end up falling off a cliff. Think about a bathtub full of water with a kid. You can get the waves going really high. You don't want to do that. So there's a real worry about time-based congestion becoming a huge problem. So where do we see all this kind of phenomena? Well, where you would sort of expect. We see it in our cellular networks. We see it in our 802.11 networks. It's present here. It's present, I think, in the Wi-Fi network, I think, though I'd like to plug directly into the Ethernet, and the router, the wireless router here is just to make sure, but almost certainly I have a good enough signal that it's going to be in that next hop. You can have problems again at the head end of your broadband gear. You can have it in any piece of the internet that's not running with queue management that is overloaded. A number of years ago, when I was working at OLPC, we were seeing 20-second latencies to the Ministry of Education in Peru. This is the classic stuff from the 1990s. But it's appearing in these new areas where we didn't think it applied. It applies, okay? So let me just run you quickly through some numbers. I think you can read this as well as I can. So just think about what happens when you have some number of nodes and you're getting a 25th of that share. You very easily get into latencies. So these statically sized buffers are clearly wrong. But of course you might not just be buffering a single packet, but 20 packets, or right now 1,000, plus maybe another 250 on each of these nodes. So the latencies can go very high, not to mention you can get problems from the retransmit insanity. Then, of course, you can have really spectacular failures like we did at OLPC that maybe I'll talk about tomorrow. You get a really ugly sight, which you often have suffered from. Maybe not so much at this conference, but I'm sure you've been to conferences where the wireless network is useless completely, and you sort of wondered why. Schools, hotels. Hotel wireless networks are usually bad in my experience. Very often, of course, you've got an uplink that's the wireless router is 3 walls away, so you're down at 2 or 4 megabits per second over that last hop, and so if they have a higher bandwidth hop, you've just lost. So the moral out of all of this, we had all sorts of OLPC problems, but despite trying to understand what was going on, we missed Bufferbloat entirely in our failure analysis, what was happening. I can tell you what else we did identify at the time, but I missed it completely. So the thing to remember is buffers are only detectable at a saturated bottleneck, on either side of a saturated bottleneck. The queues don't build all over that path, so long as the packets can get out faster than they're going into a given node, you'll never see the fact that there's buffering there. So this is a more exhaustive list of things that you may have. You have to even think about switches in this. A gigabit switch has of order 8 milliseconds worth of packet buffering in them, and they have to. Nature of the beast. Well, where else may you find things? Well, I started running smoke ping inside of our network and saw some interesting spiky latency that would come and go, and I seemed to be much more excessive than I was expecting. So I checked with our IT department, and we're using various quite sophisticated classification schemes to make sure our VoIP goes around our corporation just fine. but no queue management. How many of your corporate I'd love to have you go back to your corporation or other organization, find out if you've got, let me know if you're running queue management or not. Then there's various kinds of middle boxes where so when I started looking at things, I noticed that I was having problems at what looks to be where my IPsec tunnel would land in Alcatel-Lucent. I would expect to find it in firewall relays. I mean, it's a mistake we are all making. So, where do they hide? Well, nearly everywhere is the answer. You don't notice them except when you're saturated, when you have a link saturated. But even a single TCP connection, with the exception of on Windows XP, which doesn't have Windows scaling turned on by default, can saturate anything out there these days up to a gigabit without even trying, without even breathing hard. It just takes long enough for it to do so. I can explain offline what, it takes a while for TCP to saturate a buffer, but it will. And it's been known for a long time. The last major topic I want to talk about is what the browser speed wars have been doing to us. So initially, the HTTP 1.1 spec, RFC 2068 that I edited and the like said no more than 2 connections over the same path. Currently, as far as I know, Chrome opens up 6. Firefox is 15. And so it's really easy to end up with a pile of packets in flight, right? Except there's now a proposal to increase TCP's initial congestion window. So Google has actually upped its initial window to 8 packets. Though Vint has been talking to them, maybe they've turned it back down. I'll be interested to find this out. It'd be nice if I had time to test between now and the IETF. The last I knew, Microsoft had turned off the initial congestion window altogether. So if you hit a page with a pile of images in it, your Firefox is going to open up 15 TCP connections, and as fast, if you hit a pile of images in memory on Google Images or Microsoft's image server, you're going to have a lot of packets flying effectively all at once at your poor broadband connection where they go splat. These things are dumb devices. We can't get VoIP around these things. Okay? These days they shouldn't be dumb devices, but they are. There's no classification in your typical broadband gear. They're just FIFO devices. So I think right now this proposal to up the initial congestion window is a bad idea. In fact, I would argue that we should have serious discussions with the browser guys and the like real soon to get it back down to something more reasonable. Because I would certainly like to be able to do something else than web surfing without transient problems, like my telephone conversation, right? The right solution, of course, is HTTP also sucks, and we should replace that. This idea that you're opening up 15 connections to try to make things go fast is a result of the fact that HTTP is such an ugly protocol that pipelining has ended up failing for reasons I don't have time to go into here. There are some fascinating network neutrality questions. The first of things you need to think about. Number one, BitTorrent. The BitTorrent problem almost certainly triggered the whole issue. And what people don't tend to understand is, I believe, that the ISP's call volume was going up at a frightening rate and they did not understand it. Now, for various reasons, Comcast happened to have the worst ratio of downlink to uplink bandwidths and hurt the most. XP, since it has the small congestion window, particularly when you think back about 5 or 6 years, would typically not trigger this because you'd never have more than 64 kilobytes in flight at once. You'd never see the insane things I've seen. But there's interesting problems as a result of this. It turns out that in all 3 of the technologies, the ISPs provision voice in a completely separate channel than data. So they have, in effect, a form of classification that you don't. So their telephony can be made to work. Right now, VoIP bought over your data service, basically, if the devices are the way they typically are at the moment, is never going to work well. I don't think that this was understood. I don't think there's any grand conspiracy out there at all. The consumer ISPs take it on the chin every day by the service calls that they cannot resolve. That costs them money, direct bottom line profit every time the phone rings. They didn't intend for this disaster, and it's been getting worse and worse. And I know this happens because I generated a lot of calls myself trying to make my home network work. The first thing we have to do, if we want to do any interesting innovation in the internet, we have to fix Bufferbloat. This is urgent. It's now. It's all over. I'm actually going to change this closing, because I prefer a different analogy these days. We're all in this boat together. We all have this problem. We've all been making the same mistakes again and again in all our operating systems, all of our different technologies. Please come help. Okay? Don't be embarrassed. We're all in this together, and we've all made a major problem. So in any case, I started blogging about this in late November. We now have a development website, mailing list at bufferbloat.net. Please come join. I have a much longer talk where I go into excruciatingly more detail that is up at this address. So if you had trouble understanding me, I've been trying to talk slowly. There is audio there which you can go forward and back on, and so on. So that's where we find ourselves. It's not a good situation. Just about every machine in this room has serious buffer bloat in it, which is getting you again and again, and you haven't known it. Almost certainly true on the routers too, the wireless routers.
What's the suggestion for OpenWRT?
Well, there's a bunch of things, and part of why I'm giving this version of the talk is I'm trying to do things. So our base operating systems are broken, including Linux. Okay. The idea, there's a fundamental cognitive mistake people make, which is that there is a right number for what the buffering ought to be. It isn't that buffering is evil, it's there to absorb bursty traffic. It's leaving it unmanaged so it can grow out of bound, which is the fundamental issue here. Okay? So in the in the ring buffers and/or the device drivers, and that really is a part of the device driver and hardware, we need to fix those device drivers. We need to understand that the operating system itself, for how it deals with the whole buffer management interface between the hardware and where you do traffic classification and so on, needs to go from dumb to smart, much smarter and variable. It also turns out that I can't tell you what the exact right answer is right now. So you can't, red is buggy. It sort of works in core internet routers. It will not work in a wireless environment such as we face now. It just does not. It sort of limps along in large part because of the large amount of aggregation of traffic that's occurring there. And here at the edge, we hit it with all sorts of funky bursts all the time, and it just is, we just don't have a good, there are a couple of possible algorithms we know of, one of which I'm actually running on this laptop now to try to manage the buffering to wireless. There's a paper by some, forget the guy's name. There's a group in Ireland, and I should. That's why you do run-throughs of talks, because you learn all the things you should go back and have at the tip of your tongue. And so that's very recently been put in to Linux here. Julius here has done a stochastic fair blue implementation. We need to experiment with that and see how it works. Remember, we've got an actual router problem here. We're going to really need to do real queue management in our routers, not just control the situation in our host. Because you can have multiple different things coming into a router, not just, so it's a little bit harder problem. Then there's if I can ever pry out of Van Jacobson, he thinks he has something which may work, that you can get some of the gist of by looking at the red and different light thing from 1999, but he says that's buggy too. I have something more recent on my laptop, but I haven't managed to catch him on the phone at the right time to even find out if what I have has reflected the fixes he has there. So the honest answer is some of this we really need to do fundamental work on. Maybe we have some algorithms that may work, but they are untested and not even fully simulated typically. Okay? Yeah?
Wouldn't it be an interesting idea to test algorithms like this on our large mesh clouds? Because we have the ability, we have lots of routers connected in a strange way with horrible behaving links, and we can all reflash them.
Why do you think I'm here today? Yeah, exactly. Now you understand why you got this talk.
My question is there a patch for it? Is there a patch for Linux we could test on OpenWRT if we say, okay, we do a second flash and then we see how it works?
Right, so I'm not even really, one of the interesting questions is what do you mean by works? Because what we want is an algorithm that always works. Part of the problem with red and why it isn't even universally used in core parts of the internet is that it doesn't work some of the time, okay, fundamentally. We need something that always works. So now we have to define what always is. What does the traffic look like? What are the different circumstances we need to test? So we have everything from the single machine case to the very busy overloaded conference to the regional mesh network with crossing schools and everything else. So one of the fascinating problems out of all of this, and I think one of the really big problems is going to be the testing of these algorithms. Okay, and I don't claim to have a good answer for that, but yes, that's why I came. You're in a good position to start to do this, and mesh networks are even more sensitive to this than most because you've got multiple hops, any one of which is maybe adding it, and you're very, depending whether it's mobile mesh or not, a mobile mesh, of course, has the individual links varying all the time.
The static ones have this too.
Have some, but much less. It's closer to. It doesn't vary at the instant-to-instant basis like that OLPC or any of our laptops as you walk around it, right? The time scales tend to be different.
Well, I beg to differ a little bit, like in a city.
Oh, in a city, yeah, right, sure.
The city level.
Right, exactly.
There's cranes moving in between,
Right.
whatever.
But
Moving.
right, and yeah, so that's why I came, because I knew this community is one of the communities able to quickly take some of these ideas and try them out. And I know you're hurting in a lot of places and haven't understood why. So
The problem is, I think we have lots of people having knowledge in different areas, but I'm not sure about this area, so we would need some source code to test it.
Well,
I don't think we can take the paper and saying, okay, now we are...
I understand exactly. So Julius's SFB implementation went upstream, what was it, 3 weeks ago? At long last? Yes. Now that people began to get it, the arguments went away. And, you know, I'm still trying to extract the red light algorithm out of VAM. Hopefully, I'll get that from him. The honest answer is particularly for the wireless case, we don't have turnkey solutions right now. The things we can do safely right now is things like, we know the transmit QLEN is plain orders of magnitude too big. We can mitigate the problem from the horrific state it's often in now to something an order of magnitude less, but that may still be, hundreds of milliseconds in some environments. To really get it down to where it ought to be, it's not a solved problem, and I don't want you to go away with I think it'll be a fun problem to tackle, right? We have a really meaty, important problem here.
I'm not talking about that. I don't think anyone here expects the solution at once, but right. I think there might be a lot of small networks that would say, okay, you say you might have something useful, okay. We
also need better tools. We also need better tools. So for example, the best tool right now to identify which hop has got Bufferbloat is a Windows-only commercial application called Ping Plotter. We have MTR, which sort of does the same sort of cross of ping and trace route, but it doesn't plot things up in a useful fashion, so a mere mortal can say it's which hop it is. There are other issues that we'd like to be able to deploy ECN, and debugging, we don't have good tools for debugging ECN at the moment. Though techniques of how to do that, Steve Bauer in MIT has now figured out. And so he reported on some of this at the Kaido workshop about 3 weeks ago.
The problem is, like, with the community wireless networks that we're running, if you deploy ECN, like we had it once in OpenWT, and things break afterwards, you just need to take it out again.
I understand that you may not be able to deploy it in the general case right now because there's still a lot of brokenness out there. So in fact, the worst offender that's instant, according to Steve, turns out to be the educational research networks, where there's a network here in Europe, I forget the name of it, which is like 30% is broken at the moment. That's very rapidly getting fixed. Okay. Now that we know that the problem is there, that's what I said. We need the tools so that things get fixed, to diagnose the problems and tell people your things are broken.
Can you measure the Bufferbloat when you directly have access to the router? So
I've already measured my Bufferbloat right here. It's the first thing I did when I sat down back there an hour ago.
I don't mean test it with ping for the connection, but if every router in the mesh network would have a small software detecting the spikes, we have access to the mesh. Here's another interesting idea for you. There's the IP timestamp option. There's also NTP. So Dave Todd had the interesting idea on the NTP front of, if you start looking at the noise in NTP, this starts to tell you a lot about what's going on. The noise is actually, which they've been discarding. So in fact, a lot of the NTP
observation points have been actually throwing away exactly a lot of the data we would like to have about well, we're observing Bufferbloat in this direction at this point in time. So there's a number of ideas there of how to start keeping track of what's going on, but there's tons of work to do. We have problems all over, and the biggest problem right now, and in some sense why I haven't been, I mean, sooner or later I believe this is going to go into the mainstream press, and I haven't been really anxious to trigger that in a big way, in part because I don't want there to be, until there's better things to do, like I can tell people, run this program and it will tell if your home router is broken so you can go do something about it, or it's your ISP that needs to break it so you should call up your ISP, or it's your operating system that's got problems so you should be beating up your operating system vendor. Right now we're in a situation where that will drive people even nuttier than they're already going to be. I think it's only a matter of when. I've thought it was going to happen a couple of times already this year, but so far it hasn't gone into the mainstream press. I think it's only a matter of when.
The Windows 2 that you worked on?
That one's called Ping Plotter.
Ping Plugger.
Ping Plotter. Yep. Yes, sir.
So I'm currently working on tuning voice over IP applications.
Mm-hmm.
Do you have any idea? People already tried to tune the buffer?
Well, I can tell you that Dave Todd and I, having mitigated our home broadband connections, had the most enjoyable LinPhone teleconference with each other that I can remember since I was working on teleconferencing in the 1990s a few weeks ago. Once you got your, having mitigated by using bandwidth shaping, you can cause most of the problem in your home broadband connection to be hidden. You can keep those buffers from filling. Okay? So my latencies, rather than the of order 1 second latency I was getting, are now no more than 20 milliseconds. 10 to 20 milliseconds. So I'm thinking about 10 millisecond jitter on top of on top of a 10 millisecond minimum latency that the cable stuff seems to give me. Okay, so my home now has, having mitigated it in my home router, I no longer get the internet is slow today unless somebody's in the wrong part of the house. So my router buffer bloat is kicked in.
And how does it, if I want to do voice over IP over wireless,
yeah,
on the Wi-Fi, it has it needs to have buffer tuning because the small packets.
But if your host and your router have these ridiculous sized buffers and those links ever get saturated, you've essentially lost. One of the more subtle things is it turns out we almost certainly want to do some much more sophisticated classification as well. But the right thing to think about is to fix the buffer bloat first, because you'll have a lot less problems to face and how you then classify to get the last bits of it. Wondershaper, which was done six or 8 years ago, in the face of these giant buffers appearing in the hardware, is now broken in effect, because the packets never stay in the transmit queue where they can be classified. They get immediately dumped into the drivers. And so there's a bunch of issues that need to get, we need to revisit some stuff that was worked out quite a while ago. I mean, people have noticed this on DSL for a good 6 or 8 years, okay? In fact, Dave Clark at MIT, who runs a micro ISP in Concord, Massachusetts, and so he literally has his own DSLAM to keep his hand in what ISPs are doing. And so he first ran into the big buffer problem 6 years ago and measured a 6-second latency on that DSLAM, but only knew about the one piece of hardware, right? He used it as a denial of service attack on his son's excessive World of Warcraft playing. Anytime that his son should study, you need to saturate the link, and the gameplay would stop. So once you have the conceptual understanding, all these problems that you've seen in various guises, not all of the problems, there are still other problems out there as well, but many of the problems you've seen for many years start falling into place, okay? And you can start being able to do something about them. So one of the ironic situations is you get you go out and buy a later generation of hardware, as I did with the DOCSIS 3 modem. Well, the buffers in that device, if they were thought about consciously, were sized for the much higher bandwidth that DOCSIS 3 can go. But what happens when you plug that in and run it at DOCSIS 2? And you're still at the 20 megabit per second provisioning point. You've made your buffer bloat problem and your latencies worse by running out and buying the later hardware. Okay? So